Hey guys, this video is going to be like a review over electron configuration. The electron orbitals exist in 4 different subshells. There's the S, the P, the D, and the F. And so to review the shape of those, this right here is what an S orbital looks like. It's very spherical, all right? And each orbital can have 2 electrons at max. So the S, because there is only one orbital in the S subshell, can hold 2 electrons. Next we have the P subshell, and the P subshell has 3 orbitals, right? There's Px where it's along the x-axis, Py where it's along the y-axis, and Pz where it's along the z-axis. So it kind of looks like a dumbbell along those axes, and when you put it all together, it kind of looks spherical in shape. But there's 3 different orbitals in that subshell, and so if there's 3 orbitals, that can hold a total of 6 electrons. All right, and then after that we have the d orbital, so they're up here. And you don't need to know all of the names of each orbital or even really the shape of them. It just helps kind of put all of the concepts together to see it. So there's 5 orbitals here in the d subshell. And if each orbital holds 2 electrons, that would be 10 electrons total. All right. And then the F are down here, and there's 7 orbitals, and they each hold 2 electrons. So 14 electrons total could be in the F subshell. So we have S, P, D, and F, and if they're in the same energy level, then this is increasing energy going down. And so that would be 1, 3, 5, 7 orbitals, so 2, 6, 10, 14 electrons. All right, so really quick review over simple periodic table vocabulary. All right. The groups are vertical columns. They also are known as families. All right, and so elements in the same groups have the same number of valence electrons. So group 1 has 1 valence electron, 2 has 2, 13, 3, 14, 4, 15, 5, 16, 6, 17, 7, and 18 is 8. And because they have the same valence electrons, they behave similarly in chemical reactions. So all of the alkali metals, or group 1 metals here, they all behave very similarly in chemical reactions. All the halogens, they behave similarly in chemical reactions. Noble gases don't react because they've got complete 8 electrons. And we'll talk about the transition metals, these guys in the middle, here in a little bit. All right, the periods are the horizontal rows, and they are given numbers as well, 1, 2, 3, 4, 5, 6, and 7. And just to be clear, here's number 57 on the periodic table, here's 58. So this is actually part of the 6th period. Here's 89 and 90, so this is part of the 7th period. So these numbers represent the outermost energy level of that atom. And we can usually use the letter N to show that. All right, this is known as the principal quantum number. We're not going to get much into quantum numbers, but that one is usually one that I talk about. And so an energy level, if you go back to, I don't know, 8th grade or something, whenever you were drawing the Bohr atoms, right, you would have drawn hydrogen with 1 proton, and then it has 1 ring around it, and since it has 1 proton, it has 1 electron. And so this is the ring where N is equal to 1. Its electron is closest to the nucleus. And if we look at lithium, lithium has 3 protons, so it has 3 electrons, and it has 2 in the first ring, and then it has 1 in the next ring. And so this is where N is equal to 1, and this is where N is equal to 2. So if you look right here at where lithium is, 2 is its max energy level, because that's where its valence electrons sit. All right, now let's look at sodium. Sodium has 11 protons. 2 are in its first ring, and then it has 8 in the next ring, and it has 1 in the outer ring, which is the third ring. So this is where N is equal to 1, N is equal to 2, and N is equal to 3. So those are actually energy levels. They're not orbitals, because those energy levels or shells are divided into the subshells that we just looked at. So N, the principal quantum number, is the energy shell or level. All right, and then those energy shells can be broken down into the S, P, D, F subshells. So when N is equal to 1, there is only one subshell available to it, and it's the S. When N is equal to 2, there are two subshells available, and it's S and P. When N is 3, there are three subshells available, S, P, and D. When N is 4, there's 4 S, P, D, and F. And when N is 5, you have S, P, D, and F, and so on and so forth. All right, we don't go past the F subshell. There are others, but we don't need to go past those. All right, so the blocks that you can look at on the periodic table, okay, the S block is right here, includes helium. And so remember that the S subshell holds 2 electrons because it has one orbital, and so it holds 2 electrons. All right, and then P, the P subshell is over here, and P has 3 orbitals, so it holds 6 electrons. And if you look, it is 1, 2, 3, 4, 5, 6 across. All right, and then the D block is right here in the middle where we consider the transition metals to be. And it's got 5 orbitals, and there are 10 electrons. And so if we look, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 across. And then the last one is F, and it's 7 orbitals, so it holds 14 electrons. And so that's these guys down here at the bottom, the inner transition metals. And if we count, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 across. So that's how you can remember these numbers. You just have to count the number of elements across the periodic table. And this makes electron configuration writing a lot easier. All right, so there's a few rules for writing electron configuration. First, the Aufbau principle states that the lowest energy level has to be filled first. So where N is 1 has to be filled before N is 2. And S of that same energy level has to be filled before P. All right, electrons fill each degenerate orbital one at a time and then go back and pair up. So degenerate orbitals means same energy. So degenerate means same energy. And so let's say we're looking at the 2p orbitals. So there would be 3 2p orbitals because p subshell has 3 orbitals, and these would all 3 be degenerate. All right, and so they have to fill one at a time before they go back and pair up. I don't know if you remember that, but that's what I'm talking about. Okay, so electrons in the same orbital have to have opposing spins. That's the Pauli exclusion principle. All right, so it's only 2 electrons in each orbital, and they have to have the opposite spin. So they can't spin the same direction. Okay, so 3 different types. There's unabbreviated, and that fills the orbital starting with the 1s until you get to the element that you're looking for. There's shorthand, or noble gas configuration, and that is when we fill the orbital starting with the noble gas in brackets that comes before the element we're looking at. And then there's orbital notation, and that's where we use these arrows. So I'm going to show you all 3 types for a few elements, and then we'll look at ions. First, let's go ahead and do carbon. So I want to get to here, and I have to start at the beginning. I'm going to label my periods, my energy levels, 1, 2, 3, 4, 5, 6, and 7. So I'm going to start right here at the first one. So this would be 1. Remember, this is the S block right here. So 1s. I'm going to go all the way across. 2. So the first energy level is completely filled, and it only contains the S subshell, which has 2 electrons. So this is my energy level. This is the number of electrons in that subshell, and this is the subshell designation. Okay, so we'd start off with 1s2, and then we go to the next element. So we already went through helium, so I'm going to go to lithium next. So that's 2s. I'm going to go all the way through it. So 2s2. And then I'm going to go across to boron. So that's going to be 2p, and I want to go to carbon, so 2p2. All right, and we know that carbon has 6 electrons. So if I look at all the electrons that I've put in here, it's 2, 4, 6 electrons. So that's the electron configuration for carbon, and that would be the longhand. Now, if I wanted to write the noble gas configuration for that, I would start with the noble gas that comes before carbon, because I'm looking for carbon's electron configuration, and that would be helium. Helium comes before carbon. So I'm going to put it in brackets, and what that's basically stating is that I have the electron configuration for helium inside of those brackets. All right, and then I'm going to go to the next line down. So after helium comes lithium, so I'm right here, and so that would be 2s2 through beryllium, because I have to fill that s orbital before I can go to the p, and so 2p2. And then for the orbital notation, I'm going to write out the whole thing. So I have 1s orbital, and then I have the 2s orbital, and then I have the 2p subshell that has 3 orbitals in it. And so each one of those orbitals is represented by a line, and 1s has to get filled before the 2s can get filled, and then the 2s gets filled, and it has 2 electrons in it. So these arrows represent the electrons. One is spinning up and one is spinning down. Now when I get to 2p, these 3 orbitals are degenerate, so they have the same energy. So the electrons have to spread out before they can pair up. All right, so I've only got 2 electrons there, and so now that's complete. And so that would be carbon's orbital notation. All right, so I want to look at chlorine next. So we're going to start at the beginning right here, and I'm going to go all the way from the beginning to chlorine right here. All right, so I'm going to start here. So first I have 1s2, go all the way across. I have to completely fill the 1s, and then 2s2. Then I'm going to go across. That would be 2p all the way through 6. And then after neon comes sodium, so I have 3s2. And then after magnesium, I have 1, 2, 3, 4, and 5. So that would be 3p5. So that's the electron configuration for chlorine. And if I add up all of the electrons that are here, there'd be 2, 4, 10, 12, and 17 electrons. So that is chlorine. And if I wanted to do the noble gas configuration, the noble gas that comes before chlorine is neon, right here. So I'm going to put neon in brackets, and then I'm going to start right after neon, which is here at sodium and magnesium. So it'd be 3s2, 3p5. So this neon took care of all of neon's electron configuration in here, and you have to use a noble gas. You can't use any element you want. It has to be something that's complete. And then the orbital notation would be one line for 1s, and then we have 2s, and then 2p, and then 3s, and then 3p would have 3 orbitals. So I have 2 electrons here and 2 there. 2p has 6, 3s has 2, and then 3p has 5. So I go 1, 2, 3, 4, 5. So they're going to spread out as far apart as they can before they go back and pair up. And so there are 17 arrows total, and these have the highest energy. All right, so I want to look at the valence electrons for this. So the valence shell for chlorine is the 3rd shell. And we know that chlorine has 7 valence electrons, and they're in the 3rd energy shell. So these are the valence electrons for chlorine, because this is the biggest number. So it's the valence shell. All right, now let's look at calcium. All right, so calcium is right here. And I'm going to start at the beginning again. So I have 1s2, 2s2, 2p6, 3s2, 3p6 all the way through, and then we have 4s2. So its valence shell is the 4th shell, the outermost shell, and it has 2 valence electrons in that 4th shell. All right, if we're going to write the noble gas configuration, we would have to use argon, because that is the noble gas that comes before calcium, and it would have the notation after that of argon 4s2, and that would be it. So this right here is for argon. The orbital diagram for calcium, we would have 1s, 2s, 2p, 3s, 3p, and then 4s. So Every single one of these orbitals would have 2 electrons in it. One would spin up and one would spin down, and all be paired. So if you remember, when n is 1, we just have the s orbital. When n is 2, we have the s and the p. When n is 3, we have s, p, and d. When n is 4, we have s, p, d, and f. Now, I don't have a 3d here. What happened to it? The d orbitals get filled after the 4s or 5s or whatever they come after. So what we do, the d block, is we subtract 2 off of the energy level. So this is actually here, 3d is here, this is 4d, 5d, and 6d. So it's just n minus 1 for this whole area here. And then the f, this is actually 4f, even though it's in the 6th energy level, and this is 5f, so this is n minus 2. We won't do any electron configuration for the f block, but I just wanted to remind you of that. All right, so let's look at the electron configuration for iron. All right, so iron, we'd start at the very beginning. We have 1s2, and then we have 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. So remember, you just take one off the front, and you can see it like this. Other times you might see it written like that. The only thing that has to happen is the 4s has to be filled before the 3d, but you can list all of these together because they are actually all in the same energy level. The valence electrons for iron are right here. They're in the 4th energy level because this is the highest energy level. It's still the outermost energy shell. All right, so that means that all of these will have 2 valence electrons, except for the exceptions. And we talked about those last year. They're not in the AP curriculum, but the exceptions are this group and this group. And I'm not going to get into it now, but we can talk about it in class if you want to. All right, so for the noble gas configuration, I'm going to use argon because that's the noble gas that comes before iron. And then I'm just going to go straight into the 4s, 3d6. And then the orbital notation, and I'm just going to show these two right here to save space. So I have 4s, and the d subshell has 5 orbitals. So I'm going to draw 5 lines, and I have 4s2, 3d6. So I'm going to put 1 in each orbital and then go back and pair up. And so that would be the orbital notation for iron. All right, so now let's look at what happens when they become ions. So let's do oxide, and let's also do magnesium. And then let's look at iron 2 and iron 3. Okay, so oxide means that since it has 2 negatives, it has gained 2 electrons. So I'm going to just look at oxygen first, all right, which would be 1s2, 2s2, 2p4. And so if it gains 2 electrons, it's here, and so it's going to look like neon. And so it would look like this. The electrons are going to be added to its outermost orbital. And so it just fills up that second energy level, the S and the P. So remember in 8th grade when you were filling the rings, 8 was an octet. I don't know if they called it that, but they always wanted you to put 8 in the outer ring if it was full. And so what you're really filling is the S and P orbitals. All right, and so you want a complete octet that would be its outer S and P orbitals. All right, now for magnesium, if I look at just magnesium without the charge, that means that I would have 1s2, 2s2, 2p6, 3s2. Now, it has a 2 plus charge, so it didn't gain electrons because electrons are negative. It lost electrons. So it lost 2 electrons. And it's going to lose it from its outermost orbitals because they're not going to be lost from the ones closest to the nucleus. That doesn't make sense. It would lose it from the outside. So these are the ones that are going to get lost. And so it would look like 1s2, 2s2, 2p6. So again, it has that full outer, the valence shell. So if you look at this, they both have magnesium 2+ and oxide. They both have the same electron configuration. So these are called isoelectronic. And they're isoelectronic with neon, because that is neon's electron configuration. All right. Now, if we look at iron, remember iron's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Iron 2+ is going to lose 2 electrons from its outermost shell, which is this one. So these are the electrons that have to be lost. They're not going to be lost from 3d6. So if I write the electron configuration for iron 2+, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. So the fourth energy level goes away completely because it loses 2 electrons. Now iron 3+ is going to lose those 2 electrons as well as one of the electrons from 3d. So it would look like 1s2, 2s2, 2p6, 3s2, 3d5. All right, so all of these are always going to lose from the 4th s before they lose any from the 3d. And then these in here are going to lose from the 5s before they lose from the 4d. If you need more practice, there's another video with way more examples from pre-AP if you want to go back and look through it. I'll put the link in the description.